Welcome to week 1 of Math 320. I am Professor Huang, and we begin this week with some more warm-up. Last week, we reminded you the standard sets of numbers n the naturals, z the integers, q the rationals, and r the reals. This week, we will focus on the basic properties of these sets of numbers. In particular, how we count with them, how we compute with them, and how we compare them. For the first 3 lectures this week, I will still rely on you providing an intuitive grasp of what the real numbers are. For the final lecture this week, we will finally launch into the realm of real analysis, and I will ask you to forget your preconceptions, and we will try to build for you some idea of what the real numbers actually should be. This first lecture will be on the concept of cardinality. By cardinality, we roughly mean how many elements there are in a set. Notationally, we will use card of X for the cardinality of a set X. At this point, I haven't quite told you what the cardinality is, and we will fill this in the new slides. For finite sets, there's an obvious way to define the cardinality. We will let the output of card of X to be the natural number, or 0 if the set is empty, corresponding to the number of elements in the set. So card of the set containing 0, 1, 2, and 3 is equal to 4, since there are 4 elements. And card of the set containing -1, 2, and 5 is equal to 3, since there are 3 elements. For finite sets, there is a useful combinatorial principle called the pigeonhole principle. It states that if you have more pigeons than you have pigeonholes, then some pigeons must share a hole. Or if you have more lodgers than rooms, then some lodgers must have roommates. In mathematical language, it says if x and y are 2 finite sets, with x having a greater cardinality, then there can be no injective function from x to y. Intuitively, the proof of this statement is basically what I said earlier about pigeons or lodgers. Another way to think about pigeonhole principle is in terms of its contrapositive. If x and y are finite sets, and if there is an injection from x to y, then the cardinality of x can be no greater than the cardinality of y. Based on this second equivalent statement of pigeonhole principle, we can now define rigorously what cardinality means for arbitrary sets. Since cardinality is an indication of size, we will not specify precisely what sort of thing a cardinality is. Rather, we will specify cardinality by how the cardinality or size of 2 sets can be compared. This is, after all, what size is good for. So, definition. Given arbitrary sets x and y, we say that the cardinality of x is no bigger than that of y if there exists an injection from x to y. This notion of cardinality is in some sense the correct one for measuring size, thanks to a theorem due to Cantor, Bernstein, and Schroeder. Given arbitrary sets x and y, if we know the cardinality of x is no bigger than that of y, and also vice versa, then there is a bijective function f from x to y. Let's talk a bit about this theorem. The hypothesis of the theorem, if we interpret using the definition above it, is basically saying that we assume there is an injection from x to y and separately another injection from y to x. The conclusion says that there is a bijective function f between x and y, which is another way of saying that the elements of x and y can be lined up next to each other in pairs, with every element in x having a partner in y and vice versa. And this corresponds with our intuitive notion of x and y being of exactly the same size. Thus, the CBS theorem says that if the cardinality comparison works both ways, then we can actually be pretty confident that x and y have the same size. In this case, we will say that x and y have the same cardinality. We will not offer a proof of the CBS theorem in this course, since it is more a topic of set theory and logic and is rather tangential to real analysis. Now let's look more at the case of infinite cardinality. We say a set is infinite if there exists an injective function from the natural numbers to x. To give some examples, each one of z, q, and r is infinite. We see this by looking at the function with the formula f of x equals x, with domain always the naturals, and range 1 of z, q, and r. Since any of the three sets contain the naturals as a subset, this function is well-defined and injective. A nice feature of our definition is that sets are either infinite or finite. This seems to be a strange thing to say semantically, since in English language, infinite is the opposite of finite. However, mathematically, we have made a particular definition of what infinite means in our context, and we need to check that our mathematical definition is consistent with the English understanding of the words. As an aside, this means that there can be wrong definitions. These are definitions whose connotations betray something not logically consistent or implied by the actual mathematical meaning. Anyway, we formulate this as a theorem. If a set is not finite, it is infinite. More precisely, if for every natural number n, we can show that the cardinality of x is at least n. By this we mean that if for every natural number n, for any finite set with exactly n elements, there is an injective function from this finite set into x, then the theorem concludes there must exist an injective function from the naturals to x. Now, discussion of cardinality is something of tangential interest to the content of real analysis, though it does appear at times. Here, I want to show you the proof mostly because it is the first example of what is known as a diagonalization argument. The diagonalization argument is a very powerful tool in mathematical analysis when you have to construct a new object satisfying certain conditions from an infinite collection of old objects. You should think of it as a method of proof similar to how proof by contradiction is a method of proof, or proof by induction is a method of proof, except that the details of implementation of diagonalization arguments are somewhat less formulaic, which is why it is not part of Math 299. You will see variants of this argument lots in this course. Anyway, on to the proof. Before I launch into the details, I want to remind you that for the first few problem sets, you will be required to answer any proof problems in a detailed step-by-step format. I will frequently exhibit this proof format in this course throughout the semester. This format is more verbose than the usual prose format you see in textbooks and mathematical literature, but I want you to be able to crawl before you start running. You should think of learning mathematical proof writing as learning a new language. You need to learn to compose simple sentences before you can start writing literature. In the syllabus, you can find the proof that square root of 3 is irrational, written in both formats to give you a feeling of the difference. If you will use LaTeX, as I highly recommend, for the preparation of written assignments, the LaTeX template file that I provide on D2L includes commands that make formatting proofs in this format very simple. Okay, back to the theorem. Step 1 of the proof. For every natural number, there exists an injection f sub n from the n element set 1, 2, n to x. We justify this as exactly the definition of the phrase cardinality of x is at least n. The second step is where the diagonalization happens. In the first step, we are given a collection of functions f sub 1, f sub 2, and so on. Now we want to build a new function f whose domain is n and whose range is x using the collection of functions we are given. We will check that f is injective in the next step and focus on building the function f here. What we will do is first write down an algorithm for building the function f. And we will check that this algorithm can actually succeed in building something and does not run into any errors midway. Our algorithm starts by setting f of 1 to be equal to f1 of 1. Here, f1 is the first of the functions given to us. This is well defined because 1 is in the domain of f1. Now we will proceed inductively. We will assume we have already specified the values of f of 1 through f of n minus 1. We will use this information to help us specify the value of f of n. If there are no errors in the algorithm in this step, then having specified f of 1, this algorithm will specify f of 2, then running it again we get f of 3, and so on. Eventually, for every natural number n, f of n will be specified, and the function f is defined. So how do we do this induction? We will look at the nth function f sub n from the given list. We look at the n values given by its output. Remember that the domain of f sub n is the finite set of the first n natural numbers. We strike from this list every number that has already been used as one of f of 1, f of 2, and so on until f of n minus 1. And we define f of n to be the first remaining element of this list. This step is fairly simple to implement. The only possible problem is to justify that after striking f of 1 and f of 2 and f of 3 and so on until f of n minus 1, that our list of numbers have at least something remaining. If there are no members of the list remaining, then we cannot take the first one. Luckily, since we know that f sub n is injective, we know that there are n distinct elements in the list fn of 1, fn of 2, and so on. Since we're striking at most n minus 1 elements from it, there will be at least one left over. So this step will succeed. The reason we took this roundabout way of defining f is because that the given functions may have f sub 1 and f sub 3 very different. In particular, there is no guarantee that f of 1 appears in the list fn of 1, fn of 2, and so on. So it is quite possible that in the striking step, we strike significantly fewer than n minus 1 elements from the list, leaving rather more than just one element. To conclude the proof, we need to show that f is injective. We will do so by showing that if n and m are distinct natural numbers, then f of n and f of m are different. Since n is not the same as m, one of them is bigger, and we can take it to be m, otherwise we'll just swap the labels. By our construction, f of m is chosen to be different from f of 1, f of 2, all the way to f of m minus 1. Since n is a natural number smaller than m, it is one of 1 through m minus 1, so f of n must be different from f of m. This concludes the proof, and also this lectures. See you next time.